Welcome to Chibuzor Mathphysics. This will be the second part of this series, and we are dealing with quantum mechanics computations. In the previous video, we talked about the uncertainty principles and the Pauli exclusion principle. Now we are going to dive into computations, and this question, we start with question number 3. Question number 3. And question number 3 tells us to calculate the energy of the initial state and that of the final state and determine the wavelength of the radiation that is emitted. Stay tuned and enjoy these computations. So we are to calculate the energy of the initial state and the final state of an electron, and then determine the wavelength of the radiation emitted. So let's have the solution. So what we are given in the question is the initial state, and the initial state is given by n to be equal to 5. The final state n is equal to 2 according to the equation. The initial state is 5, the final state is 2. Using the formula that we know when we are dealing with calculation of this energy and determining the radiation emitted, we shall use this formula. En is equal to negative 13.6 eV electron volt. Multiply this by 1 divided by n squared. Of course, n here initial state is 5 and the final state is simply 2. So this simply means that n at 5 will be negative 13.6 electron volt multiplied by 1 divided by n. In this case, it is 5 squared. If you multiply this, you will get negative 0.544 electron volt. And let's compute for the final state, which it is 2. This is negative 13.6 electron volt. Multiply this also by 1 divided by 2 squared. In this case, it is 2, so 2 squared. This will give us negative 3.4 electron volts. Plug it into your calculator, and that's what you get. At this point, because our target is to calculate the energy of this state, so since we are calculating the energy, let's get the magnitude of this state. And to get the magnitude, we take the change in energy and take the modulus. So this will be the final state, which is e to the 2 minus the initial state, which is 5, and this gives us negative 3.4 electron volt, which is the final state, minus we also take the initial state, which is negative 0.544 electron volt, like we have here. But since it is the magnitude, so we ignore the negative sign. So simply take this minus this, and this will give us 2.8 4.56 electron volt. But now we need to do away with this electron volt, so we have to multiply by the constant 1.60 times 10 negative 19 joules. So we simply going to have 2.856 electron volt multiplied by 1.60 times 10 negative 19. Divide all these by 1 electron volt, so that electron volt goes with that. So we have this, will cancel with this, multiply this by this, we will have, let's have this down, that will give us 4.58 times 4.58 times 10 to negative 19 joules. Let's take a brighter color. Let's remember we are also to calculate the wavelength. If you go back to the equation, we are to calculate determine the wavelength of the radiation. Of course, we've calculated the energy of this initial and final state. So now let us determine the wavelength that is emitted, or the wavelength of the radiation emitted in this particular equation. So to calculate the wavelength, which is given by lambda, it will be equals to hc divided by the change in energy. Of course, h is a constant, and c, which is the speed of light given by 3 times 10 power 8 meter per second, is also constant. So what we have will therefore be, to get the wavelength, simply plug in the value for h, which is usually given, and the value for h is 6.63 times 10 to the power of negative 34. Of course, it is joules per second. This is joules per second. Multiply this by the speed of light given by c, which is 3 times 10 to the power 8 meter per second, so that this and this will cancel. Now divide all these together by the change in energy, which is this, and we got the change in energy to be 4.58 times 10. So we have 4.58 times 10 to the power of negative 19 joules. So if you plug this in your calculator, you will simply get 4.34 times 10 to the power of negative 7 meters. Or you can convert this to nanometers, so that our final answer becomes 434 nanometer nm. And this is how you will deal with the computations that involve calculating the initial state and the final state of an electron, and therefore after that you can determine the wavelength emitted by the same number of states that you were given. So let us see the next question in this practical questions that we have. We are to determine the frequency of a photon needed to raise an electron in a hydrogen atom. N, which is the initial state, is 3, and N in this case, which is the final state, is 5. You can pause the video and try doing it yourself. Now, just like what we did in the first question, we calculated the initial and the final state. We find the difference in energy by taking its modulus, and after then we proceeded to find the wavelength. But in this case, we are not looking for wavelength, we are looking for the frequency. We are looking for the frequency. So let me show you what to do. So in this case, let us calculate the difference in energy. So En, which is always given by negative 13.6 eV multiplied by 1 divided by n squared. This will implies that for the initial state, E was given as E3 to be equals to negative 13.6 eV. Multiply this by 1 divided by 3 squared. This will give us negative 1.51 eV. So when it is E, the final state is 5, so it is simply E5, which is negative 13.6 eV. Multiply this by 1 by 5 squared. This will give us negative 0.544 eV. So taking the difference in energy, the modulus of this will simply be E5 minus the E3, which will be negative 0.544 eV. Minus becomes plus, or ignoring that negative sign, so that you have 1.51 eV. This will give us 0.966 eV. Now multiply this by 1.60 times 10 to the power of negative 19 joules. Divide all this by 1 eV, so that this will go, and we have the change in energy to be 5456 times 10 to the negative 19 joules. This is what we have. So at this point we are looking for frequency, because this question is a bit different from the question number 3, where we are simply calculating the energy state and then we found the wavelength. So in this case we need to find the frequency. So the frequency will be given by HF to be equals to the change in energy, and we know that H is a constant, but frequency is what we are looking for. So this will simply be the change in energy, which is equals to HF. I simply change this, swap, take this to the other side, so that we know that the change in energy in this case was 1.5. If we approximate this, it will become 1.55 times 10 negative 19, and this will be equals to H is 6.63 times 10 to the power of negative 34. Of course we don't know F. F is the frequency, so multiply this by F, so that now to get F, divide both sides by 6.63 times 10 negative 34. This is 6.63 times 10 to the power of negative 34. Cancel this will go, so when we put this together we will have 2.34 times 10 to the power of 14 hertz. This become hertz, and this will be the frequency that we are looking for. And this is exactly how we calculate the binding energy, or how to determine the frequency of a photon that is needed to raise an electron in a hydrogen atom from this state, and this will be the frequency. Hope you have enjoyed the video. I remain your friend Augustine Chibuzor Galagash. Catch me in the third series of this calculation in quantum physics. God bless you.